Hi, everyone. My name is Alec. I'm a postdoc in the Scalable Solvers group. And today I'm excited to talk about some of the work we've been doing on simulating 2D quantum systems using tensor networks. So by simulating quantum system in this context, what I mean is computing solutions to the Schrödinger equation. And the Schrödinger equation, depending on how the Hamiltonian is constructed, can represent many different physical phenomena that are important for several different areas, from chemistry to materials, quantum computing to energy. And so for advancing all of these fields, it's important to have scalable algorithms for computing solutions to this equation. The challenge for computing solutions to this equation is due to the sheer size of the solution space. But to illustrate this concept, let me describe a simple setup where we have a one-dimensional lattice, and each site on the lattice hosts a single spin that can be in two possible configurations, either up or down. Then a solution to this equation assigns a single complex number to each possible configuration of the lattice, of which there are 2 to the L. And if we consider the solution as a vector, then this vector has 2 to the L elements, and numerical algorithms for computing this vector clearly scale exponentially with respect to the lattice size. Tensor networks offer a more scalable approach that allow us to compute solutions on larger lattices, where the idea is to represent the solution as a product or as a network of smaller objects called tensors, where the size of these tensors determines the amount of entanglement that we can represent in our system. So this allows us to represent solutions on larger lattices, provided the entanglement we have is relatively small. And tensor networks have been incredibly successful at simulating 1D quantum systems, but the situation becomes more complicated and more difficult when we have 2D quantum systems. That is, Hamiltonians describing interactions on two-dimensional lattices. And the reason is because each side of the lattice now has more neighbors, and therefore the entanglement structure of the site of the solutions we're interested in are more complicated. Nevertheless, a promising approach is to use a tensor network ansatz whose connectivity reflects the underlying geometry of the system. For 1D tensor networks, there's a well-established set of algorithms and software that one can think of as being built upon a foundational algorithm called density matrix ring normalization group, or DMRG, introduced in the early 1990s. However, for 2D tensor networks, it's fair to say that it's a lot more research is needed in the space of algorithms and software. And this is where the work I'm presenting today is situated. I'm going to present a few contributions that we have made to the space of 2D algorithms for tensor networks. So one way to develop new algorithms for 2D tensor networks is to take what people already do for 1D tensor networks and figure out how to generalize these ideas to two-dimensional networks. And in 2020, Zolotel and Pullman generalized this key concept from 1D tensor networks called canonical form from one-dimensional tensor networks to two-dimensional tensor networks. And the idea of the canonical forms is to ensure that every tensor in the network, except for one of the tensors, is called an isometry, which means that contracting this tensor with itself or its complex conjugate gives you an identity. And this type of relation greatly simplifies calculations that one needs to perform during tensor network algorithms. So it's upon this two-dimensional isometric tensor network ansatz that we have built our new algorithms. The first algorithm that we developed is for computing excited states of two-dimensional quantum many-body systems. So the Schrödinger equation is an eigenvalue problem with many solutions. The solution corresponding to the smallest eigenvalue is called the ground state, and its eigenvalue is the ground state energy. And the next largest eigenvalue is called the first excited state energy. And for many applications, it's of interest to compute not only the ground state, but also the first excited state or first several excited states. So we proposed a tensor network ansatz for this task that incorporates the isometric tensor constraints together with a block of tensors in the orthogonality center of the network, which allows us to represent multiple vectors at one time. We then optimize this tensor network ansatz towards the ground state and first excited states. Here you can see how the error scales for a transverse field Ising model as a function of the lattice size. So we're going up to lattice size 12 by 12. That's 144 sites. And you can see that we get reasonable error. Well, I guess my y-axis is covered, so maybe not. The error is around 10 to the minus 3, 10 to the minus 2. But what you can see is the scaling is more or less linear with respect to the lattice size. And this is what one hopes for with tensor network algorithms. And it stands in contrast to the exponential scaling that one has with state vector approach. The second algorithm that we developed on top of this ISO-TNS framework is about sampling probability distributions given by Born's rule. The Born's rule states that the probability of measuring your quantum system in a particular configuration is given by the squared modulus of the wave function. This is a very high-dimensional probability distribution, and in general, it's very difficult to sample from it. And in the case that the wave function is provided to us as an isometric tensor network state, we developed a scalable algorithm for drawing independent samples from this probability distribution. This type of sampling task has applications in quantum advantage experiments and also in tensor network algorithms that incorporate Monte Carlo. Here you can see a demonstration of the sampling algorithm, where on the left, we're showing the exact distribution that we're sampling from. This is generated by a random circuit on a 3x3 lattice. And you can see an empirical distribution that we obtain after drawing many samples using our proposed algorithm. On the right, you can see the error of these empirical distributions that we obtain from our sampling algorithm as a function of the number of samples. And you can see different empirical distributions using different bond dimensions. So this is the number of degrees of freedom in the tensor network, or the amount of entanglement we can capture. And as we increase the bond dimension, we recover the 1/n scaling that one expects of Monte Carlo sampling algorithms. A third thing we've been doing is an application of the proposed sampling algorithm for computing thermal properties of quantum many-body systems at finite temperature. So here we are showing how that we've incorporated the sampling algorithm in a workflow called minimally entangled typical thermal states, or METS, which allows us to calculate observables such as energy at finite temperature. We are showing here results for a 2x2 and 3x3 transverse field Ising model. And we observe good agreement of the proposed isometric METS algorithm against a reference values computed with exact diagonalization. To finish, I want to summarize the three contributions that I've mentioned today towards algorithms for 2D tensor networks built on ISO-TNS. The first is a new ansatz for computing excited states. The second is a scalable algorithm for sampling probability distributions given by Born's rule. And the third is an application of this sampling algorithm to compute thermal properties of 2D systems. These collection of techniques are new ways that we can explore quantum many-body systems, and I'm excited to see how they're used in the future. Thank you.